All right, this is a physics video coming at you live from Columbus Grove Physics Classroom. And for those of you watching at home, thanks for joining us. So today we're going to talk about momentum. And another way to say, I'm going to go ahead and pause the video. Okay, so we just had a quick discussion on what do we think momentum means, and the answers that came back are you've got progress, you're moving and it's hard to slow you down, and that's actually pretty close to the actual definition. We can think of momentum as red, as mass in motion. Mass in motion. And we've already talked about this a little bit. If you think about our equation for force, we're talking about mass times acceleration. Well, the motion that we're talking about is velocity. So when we're doing momentum, we're talking about mass and velocity. Mass and velocity. So our equation for momentum, the symbol is the letter P, lowercase, because we've already used M for mass. So we don't want to have two M's. And I think this derives from like the Latin word for momentum. I don't know. I used to know, I don't know now. But our formula is going to be momentum is mass times volume. So the next question I would pose to you is, if you had the choice of standing in front of a semi-truck, jumping out in front of a semi-truck that's going slow, or jumping out in front of a bullet that's going fast, which of the two would you choose? Or would it make a difference? So I got one of those. What does that mean? It really wouldn't make a difference because they have the same momentum. So we're talking about a small mass going really fast in terms of a bullet, or a large mass going really slow in terms of a truck. Doesn't matter. It's going to do the same thing to your body. So don't do either. What did you learn in physics today? Don't jump out in front of a truck. But one of the things we talked about there was the fact that we're talking about a collision. And so when it comes to the chapter on momentum, we're going to be dealing with collisions all the time. What's my unit going to be? So usually we would stop and do discussion, but for the sake of the video, we're just going to walk through it. Well, we know that mass, so we look at the unit for mass, that's kilograms. We look at velocity, that's meters per second. And so our unit for momentum is a kilogram times a meter divided by a second. And this is one of the rare instances where they take a derived unit and they don't rename it. They don't give it a new name. So for example, when we took mass times acceleration, we had a kilogram meter per second squared. And that one we rename it as a Newton. When we look at power, which is work divided by time, we rename that as a watt. They just left this as kilogram meter per second. And that's our unit for momentum. All right, I'm going to switch colors because this is the most important part of talking about momentum. It's a vector. And you wouldn't think that that's going to make that big of a difference because we've been dealing with vectors all year, and yet it does. And so this next problem illustrates the importance of remembering that momentum is a vector. And I'm going to say this every day that we talk about momentum. This is the hardest test that students take, not because the material is that much harder, but because everybody forgets momentum is a vector. So let's drop down to our first sample problem, and I've got a little diagram here. What is the change in momentum for each of the objects if they have a mass of 1 kilogram and they are traveling at 4 meters per second? And if you're watching the video at home, I want you to pause the video and I want you to look at this and think about it a little bit. I'm going to do the same thing here in class. Shoot, I need to do that. Go away. And I can't get it to go away. Go away, go away. Okay, pausing the video. All right, welcome back. So the class voted, and actually this physics class did what no other class has done. They all voted for the ball. Well, let's look mathematically and see why that's the case. So one of the things that we have to make sure that we do for this is we have to give ourselves a coordinate system. So back when we were doing forces, a lot of times I would get sloppy. I wouldn't write our coordinate system on the diagram because we're always moving in the same direction. And so you can kind of get away with not having a coordinate system indicated. In momentum, if you don't have a coordinate system, you're in trouble because you live and die by your signs. And this problem is going to illustrate why. So we're going to say that delta P, the change in momentum, is P final minus P initial. And we've seen this before. We know that when we do the change in something, we take the final value minus the initial value. So if we combine this with our formula above, we're going to say that this is mass times the final velocity minus mass times the initial velocity. So what are my velocities? All right, I'm going to ask for a participation question here. What's the velocity of this bear on this leg of the journey? Okay. Yes, we've got -4 meters per second, and down here we have 0. So the ball is also going to be -4 meters per second. What's it going to be here? +4. When I calculate, so these are the final, these are the initial. So when I go to calculate this, excuse me, if I do the bear first, delta P for the bear, I'm going to take the mass of each of these is 1 kilogram. So I'm going to have 1 times 0. And everybody just set your pencils down and watch this. This is going to be minus. This is going to be 1 times -4. So that works out to be 0 minus -4. Well, what do we do when we subtract? We add the opposite. So this has a change of +4 kilogram meters per second. If I look at the change for the ball, that's going to be the final velocity is 4. I'm going to have 1 times 4 minus 1 times -4. So this is going to be 4 minus -4. Well, if I subtract a negative, I have to add the opposite. So this ends up being 8 kilogram meters per second. And this problem perfectly illustrates the struggle that students have with momentum. You guys dealt with vectors the whole first half of the year, but they were always in the same direction. Now we're looking at vectors that change direction, and that's why we're going to live and die by our signs. Because you can see that because I went from a negative to a positive, that radically changes what I'm seeing as my change. The other example where we saw this was Atwood machines. Do you remember how when we worked with Atwood machines, you didn't put the right signage on, your solution ended up being nonsensical? Because you had to understand that when we had, if we had something going over, we had a block here, we had a pulley, we had a block here. One of these was going to have a negative acceleration and one was going to have a positive acceleration. And it's that same type of situation where the signs really do have an effect. All right, go ahead and grab your pens. You can catch your notes up now. All right, here's our sample problem. I went ahead and zoomed down. Take a second and pause the video and see if you can come up with an answer for this, and we'll come back. All right, here we go. Let's go through the answer. So we've got an object of mass of 5 kilograms travels in the positive direction with a speed of 1 meter per second. The object collides with a second object that exerts an average net force over an interval of time such that the 5 kilogram object comes to rest. Which of the following best predicts the change in momentum for the 5 kilogram object? All right, so we're going to start off, we're going to indicate this is my positive direction. So when I start off, I've got an initial momentum of 5 mass times velocity, 5 times 1. So I've got an initial momentum of 5 kilogram meter per second. And it runs into something. So that tells me that my final velocity is going to be 0. I'm going to assume that that final velocity is going to be 0. So it's going to be 5 times 0. When I find the difference, so I'm going to take my final minus my initial, that's going to be 0 minus 5. And I'm going to have a change of negative 5 kilogram meters per second. So your initial thought might be, and when we did this with forces, we talk about the force being in the positive direction. So, you know, the change is in the positive direction or with velocity, but with momentum, because we're calculating the change this way, it ends up being other than what you would think it would be. And the answer is A, negative. So we've got a negative value for that. So our takeaways today are that momentum is mass in motion, mass times velocity. And you have to be really careful when you handle this, because we're going to, like I'll probably say this a dozen more times before we're done, you're going to live and die by your signs here. We're almost always dealing with a collision of some type, and we're going to, once we get through the basics, we're going to then go through the mechanics of collisions. All right, so if you're watching from home, thanks for watching, and we'll see you in the next video.